Okay, so welcome back. Now previously in our videos we have used some features of the Arduino such as interrupts and internal timers to develop a frequency meter, and that frequency meter we were using it to measure the frequency of, in our case, the 60 Hertz wall outlet voltage provided by the power company, and it did it fairly accurately, but it used some stock code in an Arduino sketch that really we didn't discuss in detail and didn't get a good understanding of how it was working. So what we're going to do in this video is we're going to show you some of the basic concepts behind interrupts and internal timers in the Arduino so that we can better understand how that all works. And we're also going to be using that in another series, but the Arduino is also equipped with Wi-Fi, so we are putting it in a box and connecting it to the wall outlet. And that device is sending the resulting frequency measurements over Wi-Fi to our computer. So we're going to start out by using that frequency meter, and we're going to look at the basic concepts to see how it's all working. So here I've got two cycles of a sinusoidal waveform. Let's say it's your wall outlet voltage or whatever. And we need to figure out how can we measure the frequency of those sine waves. So there's a couple ways you can do it. Now you might think, well, frequency is cycles per second, so maybe I can start measuring the cycles and wait for a second and see how many cycles I've counted, and that's my cycles per second, and that might work. The problem is it may not be very accurate at all, and you have to wait for a second before you get your results. And what we're going to do is we'll look at another way to do it that's probably a whole lot more accurate. So how else would we do it? Well, instead of looking at a whole bunch of cycles, we can focus in on one cycle and measure it. So how would we do that? Well, if we can determine how many seconds are in one cycle, then we can just invert that to get cycles per second, or hertz. So here we've got two cycles of the sinusoidal waveform. The first one starts here, and then you go along and it ends here, and the next one starts at the same point that this one ends. So if somehow we could measure how many seconds were between this starting point and this ending point, which is the start of the next cycle, we can say, well, there's 1 second in this cycle, then that means it's 1 cycle per second. So we would like to have a way that we can accurately measure the time between the start of a cycle and the end of the cycle, which is the start of the next one. Well, one way would be to determine what's unique about this cycle starting and ending. Well, you can see here that it's unique that it is the only place where it is rising, crossing zero, the 0 point, and it's a rising wave. And we never see that again until the next point. So if we could figure out what point is it rising, then we can say, hey, we can have an interrupt, or if you're familiar with other software, an event, where it says, hey, we just detected that the waveform is crossing 0 and rising. That means you can start counting and figure out how many seconds between this rising and the next time you get an indication that there's a rising point. And we could have like events or interrupts that occur at each of these rising points. And in between those, we could be counting how much time is transpiring. So how would we do that? Well, if we could detect this rising 0 crossing, we could like start a timer. And the timer could start counting 1, 2, 3, 4, 5, 6, and then when we get the next rising indication, the next event or the next interrupt, it can stop the counter and say, okay, how many counts have happened in that time? And if we know how fast those counts were happening, we can figure out how many counts per cycle. And if we know how many counts per second, we can figure out how many seconds are in this cycle and just invert that to get hertz or cycles per second. So you can start to see we need some way to determine a rising 0 crossing. And we need to generate like an event or an interrupt that starts some code that starts running a timer. We just start counting values, and then we get the next indication of a rising crossing. We can stop it and figure out, we can grab the number of counts and then from that we can figure out the frequency. So that's going to be the basic design of how we can count frequency with our application. Now what I've done is I've put together a simple C# application to kind of give us a graphical view of how it's working under the hood. And what I've got here is just basically a counter. And I've got a start button that starts the counter. I've got an end button that stops the counter. And this value here is going to be how many counts have happened since I hit the start button. And here we can have the users determine how many counts we want per second. It's going to default to 20 counts per second. So I can start it and you can see 20, 40, 60. So it's about 20 counts per second. And if I hit end, we have now determined that between the start time and the end time, we got 117 counts. And we measured that at 20 counts per second, 117 counts happen in 5.85 seconds. So if that start was initiated by this first zero crossing and the end was initiated by the second zero crossing at the end of the cycle or the start of the next cycle, you can see that we have measured 5.85 seconds from the start to the end. And if you invert that, we get 0.17 cycles per second. 5.85 seconds in one cycle, which means 0.17 cycles per second. So if we know the count that has transpired from the start to the end, and we know a good indication of how many counts per second, we need to have a very reliable and accurate counter. But if we know that number, we can figure out, okay, 117 counts with 20 counts per second. That means it took 5.85 seconds to get these 117 counts, which means the measured frequency is 0.17 hertz. So I can change that. I can say 200 counts per second and start it. And you can see we can specify the count. Wait a minute, what happened? It was counting away and suddenly we got this overflow. What does that mean? Well, one of the things you need to remember is that a counter is basically a number. And it can be in the computer world like an 8-bit number or a 16-bit number or a 32-bit number. So for example, if it's an 8-bit number, it's got 8 ones and zeros. With 8 ones and zeros, you can only represent a maximum of 256 numbers. You can only set those 8 bits up to a point where you get 256 possible numbers. So what happened was we were counting, but it's only an 8-bit number and it overflowed. So you have to be conscious of your counter. What's the capabilities? Is it just counting an 8-bit number? If so, you got to be careful or else you'll get an overflow. And what we've done here is we have an event that when it overflows past the capability of the 8-bit counter, it sends out a message. So you can start to see there are some things here we need to be aware of. We need to be able to recognize that start of the waveform by a zero crossing, and that will send a start event to start the counter. And then the next one, it will stop the counter. And so we've got 2 events going on that are going to do starting and stopping. We've also got an overflow event that recognizes, hey, if we've gone outside the bounds of our counter, we're overflowing and we need to do something about it. But at the end of the day, after this thing has ended, we're going to have to grab that number and calculate using our known counts per second to get the frequency. And that's basically what the interrupts and timers do in the ATMega328. The interrupts are basically events, and they have event handlers like you see in our C# code. And there's also a timer, and we can specify to some extent how fast the timer runs. And we'd like to have a lot of counts per second so we can get very accurate measurement. So we're going to have to specify the counts per second. We're going to have events for starting, stopping, and overflowing, and then we're going to grab that value and do some calculations. So that's the basic concept behind how the timers and events are implemented in your ATMega328. So now when we did our frequency meter application on this Arduino Uno with the Wi-Fi connection, we basically fed one signal into it, and that was the modified wall outlet voltage, the 60 hertz wall outlet voltage that we converted into a square wave. And we fed it into one of the digital pins, and all of the frequency measurement was done on this Arduino by this ATMega328P microcontroller. And it does all of the calculations and allows us to send the resulting measurement over Wi-Fi to our computer. So here is the ATMega328, and you can see right here we've got a 16 megahertz crystal. And like we showed in our C# application, we were using 20 counts per second. This is 16 megahertz, so you can use 16 million counts per second to measure your frequency. Now, I know all of the hobbyists are going to jump up and down and say, oh, I'll use 16 megahertz all the time. No, 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 no. You don't want to do that because, as we mentioned before, you can get into an overflow situation. There is the ability to fewer counts per second. Instead of 16 million counts per second, you can crank it down so that you don't overflow your limited counter. So we'll talk about that, but really it's basically these devices are processing your input waveform and measuring the frequency and sending it out. So here is a conceptual diagram for the ATMega328 showing how we can implement what we showed in our C# application. And here's the 16 megahertz crystal we just talked about. You have the ability to crank that down to a lower frequency to get lower counts so that you don't overflow your counter, and so that you better match the frequency that you're measuring. We'll talk about that. So how do you crank that down? Well, there is an 8-bit register, basically an 8-bit number, and you can set the different bits in that 8-bit number to tell the ATMega328, hey, divide that 16 megahertz crystal by, say, 8, which is what we're doing. You set this bit to 1, and that divides it by 8 and gives you a 2 megahertz counter that is counting 2 million times per second. And what starts it is what we talked about before, the start button and the end button. And those are generated. Here's your 60 hertz waveform coming in, and we've actually converted it to a square wave to make it easier. So we've got our 60 hertz square wave, and it has a rising edge detector inside the ATMega328, and it will generate an interrupt and this pulse to start the counter. So it will generate an interrupt, or in the other software world, an event, and you'll have an event handler that will start the counter. And when it detects the next rising edge for this beginning of the next waveform, it will stop that counter, grab the number of counts, and then restart it. And those are 2 interrupts that you're going to get. We will get the number of counts resulting from that. Now, in the ATMega328, that resulting number of counts is going to be called T count 1 for our timer 1 counts. And that's going to be updated every cycle as we do these interrupts. And we're going to grab that number of counts and convert it to frequency. Now, for a 60 hertz waveform, if we're going 2 million counts per second, then in the time it takes to do one cycle, or 16 milliseconds, we're going to get about 33,333 counts. So for a 60 hertz waveform, T count 1 is going to be 33,333. So it's fairly accurate. It's got a lot of counts in one waveform. And we're just going to grab that, and we're going to have to deal with these interrupts. And we're also, as we said, if this counter overflows, in other words, the frequency is too low and we get too many counts, it will overflow. We're going to have to decide what to do about that. Now, this 8-bit register you can think of as what we had on the board where we're setting the dip switches to program and to operate the ATmega and the ESP8266. It's kind of like having an 8-bit register and the 8-bit switches, where you basically just set one of the switches. In our case, the second switch is going to be set to 1, and that's going to tell the divide by function to divide by 8 to give us 2 megahertz. So really, it's nothing fancy. It's just an 8-bit number, kind of like an 8-bit dip switch. So let's take a look at the sketch for the ATMega328 and see how we can implement this. So here is our sketch for the Arduino for the ATMega328 that takes in the digital line voltage signal, calculates the frequency, and in our case it's going to send it over Wi-Fi. So it says this ATmega sketch every 0.1 seconds counts the number of 2 megahertz pulses in one period of the square wave appearing at the D2 pin, converts the count into a frequency value, and sends that 60.00 string to the ESP8266 over the serial connection. So this is what we've had before when we did our frequency meter. Nothing has really changed. I just add some clarifying documentation. So we're going to establish serial communication, serial begin 115200 baud. This code uses an internal timer, timer 1. Now there's 3 timers, but we're using timer 1 to count at a rate of 2 million counts per second, or 2 megahertz, between rising edge pulses. Since the internal counter clock is 16 megahertz, that crystal, we apply what's called a prescaler of 8 to divide that count rate to get 2 megahertz. So that divide by 8 is called a prescaler. So for a 60 hertz signal, the timer count for one cycle is 2 million divided by 60, or 33,333 counts like we talked about before. Now there's a couple registers, one we're not going to use. There are 2 main registers, which are basically those 8-bit numbers, or like 8-bit dip switches, that have to be configured for either PWM or to set the prescaler value for the counter. To do this, we just set the appropriate bits high or low. The register we're not going to use is called TCCR1A. That deals with the pulse width modulation, so we're going to set that to 0 since we won't be using it. So TCCR1A equals 0. Now what we're going to do is we're going to say, hey, I don't want 16 megahertz, I want 2 megahertz. So we're going to apply the prescaler of 8, which divides the 16 megahertz clock speed by 8 to get a clock rate of 2 million counts per second. This basically sets the appropriate bit in the 8-bit timer 1 control register B, also called TCCR1B. And the bit we're going to set is called clock set 11, or CS11. So there's 8 bits, we're going to set just one of them to 1. Now to do that, we're saying TCCR1B, and we're using this format to set this CS11 clock set bit to 1. Now, one of the unfortunately non-intuitive things about this is when you execute this line of code to set this bit and set the prescaler, you are also turning on the timer or the counter. You're enabling it. We haven't finished setting it up, but it's all ready to go and the timer is running. And then we are going to preload the counter. We said TCount1 is going to be the one that gives us how many counts each cycle that we can convert to frequency. We're going to preload that to 0 to reset it. So start our counter at 0. And then we're going to enable the overflow interrupt. Again, we said, hey, if you overflow the counter, like if we go past 256 counts for a 8-bit counter, it's going to overflow. So we want to be notified of that. So we're going to enable the interrupt, which is TIMSK1 equals 1. And then we're going to clear the int0 flag, which is the interrupt flag, interrupt 0, which we just enabled. We're going to clear that using EIFR equals 1. And now we have to define that we want to have some zero crossing positive going events and what code we're going to run to start the timer or to grab the data when we reset the timer. And this is the most important part here. We define the interrupt, define that the interrupt will be initiated by a rising edge on digital pin 2, and the interrupt service routine function that will be called, and we're going to call it timer1_get. What this is saying is that when we get a rising edge on coming into digital pin 2, it will generate an interrupt, and it will call this event handler or interrupt service routine, which is the same thing as an event handler, and it will run that code which will reset the timer and start it again. and we say we want an interrupt on a rising edge from digital pin 2. So this is what defines the rising edge and what code we're going to execute. Again, nothing more than an event handler in other code. So we're going to have an unsigned integer, which is the clock count that we're going to grab. TMR1, we're going to set that to 0, and then we're going to define period and frequency, which we're going to calculate from those counts. So this is the function, this is the event handler or the interrupt service routine that gets called every time we get a rising edge detection. Again, it's this method we specified. So when we get a rising edge, we run this timer1 get, and what it does is it grabs that tcount1, which is the latest count, how many counts in one period, and we're setting TMR1 equal to that, and then we are zeroing out that count so we can start again. And we've saved that TMR1 value. So this has got the latest count, and we're resetting the timers to restart. Now we also have another interrupt. We talked about if we overflow, we want an interrupt to let us know. And what we're going to do with that interrupt, if we overflow, we're just going to zero out the timer 1. And this is a standard overflow interrupt format. Interrupt service routine with timer 1 overflow vector. And this just says when we get an overflow interrupt, it will come in here and set timer 1 equals 0. It will reset that count and we can start again. And now in the loop, all we have to do, we don't want necessarily every cycle to grab the value. We've got a delay, so it's every 100 milliseconds or 1/10 of a second. And all we're going to do is grab whatever is in that timer 1 value, the count, and assign it to this unsigned value. And in our case, if it's a 60 hertz signal, it'll be like 33,333 or something like that. And then if that value is 0, we're just going to say the frequency is 0. Otherwise, if it's a legitimate frequency value, not 0, all we have to do is take our 2 million hertz or 2 megahertz, divide it by that 33,333, and that will give us the frequency in hertz. And then what we're doing is we're doing a serial print line, whatever the frequency is, and 2 decimal points, and that's it. So all we're doing is every 1/10 of a second grabbing the value and printing it. But that's the basics of how this timer and the interrupts work. Again, pretty straightforward. It can get kind of confusing with the different variables, but really comes down to picking the pin you're going to sense the signal on if you want a rising edge, and then run to this timer get, which is kind of like an event handler, and just grab the latest and then reset and go. So that's about it for this. If you like any of these videos, I encourage you to hit the like button, subscribe, hit the bell notifications. But most of all, please let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.